Okay, let's continue. So as I told you, sound propagation means this vibration strikes the particle and the particles transfers the energy from the source to the listener. Okay. Now as I told you, imagine a situation in which there is no particle between the listener and the bell. What will happen? If there is no particle between the listener and the bell, the energy, the vibrational energy, the energy that this bell is producing by vibration, this cannot transfer this energy to the listener. Okay. So it means if there is no particle, now what is no particle? No particle means vacuum. Okay. What is no particle? No particle means vacuum. So if there is vacuum between the source of the sound and the listener, then the energy will not be able to transfer from the source to the listener. That is, the sound energy will not be able to transfer. Okay. So what I can say, the most important point is sound needs material medium for propagation. Okay, sound needs material medium for propagation. It means there has to be particles present. It do not matter whether the particles are of air, that is a gas, or liquid or solid, but the particles has to be present between the source and the listener. Then only the sound can propagate. Otherwise, sound cannot be propagated, okay, or cannot be heard. So sound needs material medium for propagation. That means sound cannot travel or propagate in vacuum. Sound cannot propagate in vacuum. Now, how is it possible? Why sound cannot propagate in vacuum? This reason is very simple, that there is no particle. So can we perform this experiment? How we have judged that this happens, that sound do not travel in vacuum? For that, we will perform a very simple experiment which helps us to understand that how sound do not travel in vacuum. For example, the experiment is, what we will do is, we will take a glass jar. Okay, we will take a glass jar and we will put a valve. Okay, we will put a valve at its bottom. Okay, now what is this? What is the purpose of this valve? We will put an air suction pump. We will put a pump at this end which sucks the air out from this jar. Okay, since you know that if the jar is open, okay, if it is in this position, definitely there is air inside this jar. Okay, but what we will do, we will put a cork at the top of it, and through this cork we will connect an electric bell. Okay, through this cork what we will do, we will connect an electric bell, something like this. And this bell we will connect it to the battery. This is a key. Okay, this is K or switch. This is the battery B. This is an electric circuit. You need not to focus on how the electric circuit is formed. This is not in your course. You will study this in your class 10. For time being, just assume that this is a bell, okay, I connected it to a battery, just like you connect a bell to a battery at your home, okay, or just like you connect a battery to your remote control of your television, okay. In similar manner we have made this bell, okay. Now, so this is a bell and this is the battery. What will happen if the air is inside this jar? What will happen if the air is present inside this jar? If the air is present inside this jar, there are particles of air floating around in this jar, okay, like this. The particles of air are floating around in this jar. When you switch it on, okay, when you switch it on, when you push this key, when you switch it on, what will happen? This, okay, this hammer will going to strike this bell, okay, this hammer will going to strike this bell. And what will happen if this hammer strikes the bell? The bell starts vibrating, okay, the bell will start vibrating like this. In this manner it will start vibrating, okay, it will start vibrating, it will start moving to and fro from its mean position, okay, it will start vibrational motion, okay, we call it as vibrational motion. So when it starts vibrating, it will start pushing the particles near it, the particles will gain the energy, they will push the particles in front of them and will come back to its mean position, and similarly the particles which gained energy will again push the particles which are in front of them, and in similar manner the sound will going to propagate, okay, the sound will going to propagate out of this bell and you will be able to hear this bell, okay. So what is happening? I did anything to this jar, I simply connected the bell, I simply connected this cork, this valve, and I connected it to a battery, okay. So when I switch it on, the bell will start ringing, I can hear the ring of this bell. But what will happen if I start removing, or if this air suction pump starts sucking air out of it, okay. So let's write this. When air is present inside the jar, if air is present inside the jar, we can hear the bell, okay. But if this suction pump starts sucking out air from this jar, the sound of this bell will going to faint, okay, the sound of this bell will going to faint, and as soon as this suction pump completely sucks out air from this jar, we will not be able to hear any sound from this bell, okay. What will happen? Let's say there are 10,000 particles at present. If the suction pump sucks out, let's say 5,000, what will happen? Only 5,000 particles will remain. Then what will happen? The sound will become fainter because the particles are reduced, okay. So we will say, if the air is drawn out from the jar, the sound of bell starts fainting, okay, it will start fainting, that is, it will start decreasing, okay, you will not be able to hear the sound, okay. It's just like when you are listening song in your mobile and you start decreasing its volume. So how you can see the sound is the song is playing, but you will not be able to hear the intensity of sound. We will say the term intensity, we will define it in upcoming classes. At time being, just assume the volume of the sound, you will feel that the volume of the sound is getting decreased. So we will say when the particles are taken out from this jar, the sound will start fainting, and there will be a situation will come when air is completely drawn out of jar. Okay, what happens when air completely drawn out from jar? The situation will become like this. Okay, this is the source of sound, this is the ear of the listener, but there is no particle between the two, so the sound that it produces will not be heard to the listener. Okay, so when the air is completely drawn out from this jar, there will be no particle to propagate sound energy. There will be no particle to propagate sound energy, and what we feel that the bell will, this hammer will going to continuously hit this bell, but no sound will be heard out of this jar. Okay, so when there is completely air is drawn out, no particle will propagate the sound energy, which means that is we cannot, or we will not be able to hear any sound. We will not be able to hear any sound because all the particles are drawn out and there is no particle which can propagate the sound energy. So what this experiment proves, okay, what this experiment proves is that sound needs a material medium to transfer, okay, from the source to the listener. If there is no particle present, then the sound will not propagate, then you will not be able to hear the sound. Now this is one conclusion. One more important conclusion that we can draw is that if the particles of air are in bulk, okay, if I increase the particles of air, okay, if I increase the particles, or we can say, for example, if there are less particles, the sound heard will be less. Okay, the propagation of the sound will be less. But if there are more particles, then the sound propagation will be more. So imagine, just compare the three types of matter, that is liquid, solid and gas. Okay, in gas there is less particles, in liquids there are a bit more particles, but in solid there are maximum particles. Okay, the number of particles in solid is more compared to the gas if we take the same volume. Okay, so what I will say, if there are more particles, the propagation of sound will increase. Okay, the sound will be propagated fast. So that's why sound travels fast in solids compared to the gases. Okay, we will understand this concept in the upcoming class. At time being, just you need to understand that this experiment proves that sound needs a material medium for its propagation. If there is no particle present, sound cannot propagate. Okay, okay, so this completes the propagation of sound. So you note this, then we will continue with the next concept. Okay, so we studied till now the propagation of sound, that how an object which is vibrating, it transmits, it transfers its energy to a particle near it, and so on. The particle by particle, the energy is transferred from a source to a destination or the listener. Okay, so this process that we understood it particle by particle. But as you know, in the air there is not only a single particle, there are billions of particles present. So definitely the particle near any bell or any object is not a single particle, it's about millions and billions of particles. For example, if I consider a bell, the surface of the bell, near the surface of the bell you will find thousands of particles, it's not like only one particle. So when the bell vibrates, it will not push only a single particle, it will apply the force, it will transfer its energy to n number of particles near its surface. So what we can assume, that when these particles are in group, let's call them a layer. Okay, so it means when a bell vibrates, it not only pushes a single particle, in fact it pushes a layer of particles. Okay, a layer of particles. So let's assume that the energy that the source of sound is transferring, it is not transferring to a single particle, rather it is transferring its energy to a layer of particle. Okay, we will assume that the energy of sound, energy of that vibrating object is transferred to a layer instead of a single particle, because that actually happens. There is no single particle, it's a group of particles which are getting energy and they are transferring it to another group of particles, and then so on the energy is transferred. So let's assume, let's take a tuning fork. Okay, let's take a tuning fork. Now what is a tuning fork? It's something like this. Okay, it's a sound producing instrument. It is something like this. It is made up of metal. Now what happened, you can hold it from this is the handle of holding this tuning fork, and when you strike it to any object, these two hands, or we call them as prong, okay, we call them as prong. These two are the prong. So when you hold it and strike it to any object, these prongs will start vibrating, okay, they will start moving to and fro like this. This hand will also move like this. So this vibrational motion, this to and fro motion of these two prongs will going to create sound, okay. So it's a sound producing object. So it means whenever you strike it to any object, any other substance, a solid substance, this will start producing sound, okay. And depending on the intensity you strike it, the sound will produce will be different, okay, the quality of sound would be different. We will understand that concept as well, okay. So as I said, this two hands or these two prongs will start vibrating. Now imagine the particles near this hand. This is the hand of this, or this is the prong. So the particles near this prong, there is no single particle, there are thousands of particles present near the hand or near this prong, okay. You will find there are thousands of particles which are present close to this prong. So we will assume that when this prong starts vibrating just like a bell, what happens when a bell starts vibrating? It pushes the particle closest to it, okay. So in similar manner, this prong will also push the particle close to it, okay, but as we can see there are thousands of particles near it. So this prong will going to push all the thousands particle, okay, all the thousands particle. It will not happen that it will push only single particle, it will push all the thousands particle close to it, and it will transfer its energy equally to all these particles, okay. It will not transfer its energy to a single particle, rather it will push all the particles close to it. So what we can assume that these particles are in the form of layer, okay. What we can see, we can assume that for explanation point of view, we can take that, let's assume the particles near this prong are in the form of layer, okay. How the layers are distributed? See, let's assume this is the medium of air, okay, this is the air. Since air is all around us, but we are assuming that this is a part of air, okay, this is the medium from which the sound will going to propagate. So the particles in this particular area is in the form of layers, okay. The layers are equally away from each other. We are assuming that the layers are equally away from each other, okay, like this, and here is the listener. Here is a listener who will going to listen the sound that is propagating in this way, okay. So at the time when this prongs are not moving, they are at rest, they are not performing any vibratory motion, these layers will be equally spaced from each other, okay. There is no difference between the two layers. See, the width of all these layers will remain same, and there is no any kind of motion or any kind of pressure between these two layers. They are simply equally spaced layers of air, okay. Now once this prong is these two prongs, when I hold this tuning fork and strike it to any object, what will happen? both of these prongs will start vibration. Okay, they start vibratory motion, and for that let's focus on only this right hand or right prong. Okay, for explanation point of view, let's focus on this right prong. What will happen? This right prong will going to move like this. Okay, that is, it will go to the left and it will come back to its original, then go to right, then come back to original, then go to left, then right, then go, then right, like this. Okay, this is a vibratory motion that this prong will going to perform. Now what will happen, how it will going to perform this motion, we have to understand this, and using this we will understand a very important concept in this propagation of sound. See, let's see that this is a position, this is the left position of the prong, and let's say this is the right position of the prong. Okay, I am assuming that this is the left position and this is the right position. Now what will happen when this prong moves from left to right. Okay, when this prong moves from left to right like this, left to right, what happens? It will push the air near it. It will push the layer of air near it. And what will happen? Since it is moving like this, what will happen? This layer, the density of this layer will going to increase. It means when it moves from left to right like this, the particles in this layer will come close to each other because its motion is like this. It is in the direction like this which is pushing the layer. Okay, for example, if I take a sponge in my hand and if I push it like this, what happens? The density of that sponge will increase. That means the particles of that sponge will come close to each other. The similar kind of concept can be applied here. When this prong moves from left to right, the particles in this layer will feel a force from this side and they will come close to each other. And you will find that when it moves from left to right, in this layer, this first layer, the particles in this first layer will come close to each other, and the density of this layer will going to increase. That means this layer will become compressed. Okay, just assume this as a sponge. When you push it like this, when you push a sponge like this, what happens? The sponge compresses and its density increases. Okay, the particles of that sponge come close to each other. In similar manner, in this layer as well, when the prong moves from left to right, it will compress this part of layer. Okay, it will compress this layer, and this layer, the particles in this layer will come close to each other, and we will say that this layer is compressed. Okay, the air inside this, the particles inside this are close to each other compared to the normal situation. That's why we will say this layer is compressed, and we will say that this is known as, this layer will be called as a compression. Okay, we call it as a compression zone or compression. We call it as a compression zone or compression. Just observe it, properly understand the concept, how it is happening. I am repeating it again and again. When it moves from left to right, it pushes the particle in this layer in such a way that particles come close to each other and this layer is compressed. Once it is compressed, it will look something like this, and we will say that this is a compression zone. It's because not only a single particle is feeling a push from this prong, there is a layer of particles which are feeling the push, and that's why the particles will come close to each other, and in this layer this will be known as a compression zone. Okay, so when it moved from left to right, this kind of compression zone is created. Okay, so let's write here, when the prong moves from left to right, when it moves from left to right, the particles of layer of air near the prong will come close to each other and a compression zone is created. Okay, a compression zone will be created when this prong moves from left to right. Now imagine the situation, now this prong is from left to right, it has moved to the right hand side, now it is in right hand side. What will happen if it move backwards? Okay, what will happen if it move backwards? When this prong moves from right to left, that is in backward direction, the particles near this prong, okay, the particles near this prong move along with this prong in the right hand direction, like this, in the left, or we can say the right direction, sorry, in the left direction like this. Okay, and we will say that the layer or the particles near this prong, that is the layer very close to the prong, okay, this layer will going to elongate. Okay, try to understand it what I am saying. See, once it is moved from left to right, it pushes the air and the particles are coming closer to each other. Okay, that is a compression zone is created. Now imagine if it moves from right to left, what will happen? The particles near this right hand side, okay, the particles near this prong, they will move along with this prong in the left direction, that is this layer will going to elongate. Okay, so the movement of prong from right to left will going to elongate the layer of air. And what will happen if the this layer gets elongated? We will say the density of this layer will going to decrease. So as we have written here, when the prong moves from left to right, the particles of the air near the prong will come close to each other and a compression zone is created. Here we will add one more point, that is density of layer will increase. Okay, and when it moves from right to left, it will elongate this layer and the density of this layer will going to decrease. Again, imagine a sponge. If I elongate the sponge, what will happen? The particles of the sponge will go away from each other and the density of that sponge will going to decrease. So a situation will come like this. When it moves from this right to, this is the left position, when it moves from right to left, it will elongate this layer and this layer will going to form like this. Okay, something like this. So what happened? They are equally spaced layers, but when it moves from left to right, the width of this layer, okay, the spacing of this layer decreased, the particles come close to each other, so it's like the formation of a compression. And when it moves from right to left, the layer gets elongated, it means the density of the layer will going to decrease. So what happens? So let's write here, when prong moves from right to left, when prong moves from right to left, it will elongate the layer of air and density of layer will decrease. Okay, that is, so here we will define new term. So when this moves from right to left, the density of air will decrease and this layer will going to elongate, and we will say this type of situation is known as a rarefaction zone. Okay, we call this as a rarefaction zone. So compression means when the particles are close to each other, rarefaction means when the particles go away from each other. That is, so when it moves from right to left, okay, right to left, it will get elongated, and that is, we will say a rarefaction zone is created. Okay, a rarefaction zone will get created in this particular area. Okay, now observe this situation. What is happening? Once it moves from left to right, it will create a compression zone. Okay, that is like this, the particles will come close to each other. Now, will the particles remain in this situation only? No, it will not happen. What will happen is, this compression zone, the particles in this particular area will going to push the particles in front of them. That is, this compression zone will push the next layer. Okay, it will push the next layer. So let's write here, where we can write is here. The compression zone will push the next layer. Okay, this compression zone will push the next layer, and slowly this compression zone will disappear and the next layer will get compressed. Okay, so it will transfer its compression, it will transfer its energy to the next layer, and this will become normal layer, and it will transfer it to the next layer, and the next layer will become a compression zone. So by the time this prong moves from left to right, it created a compression zone, and by the time it moves from right to left, what will happen? This compression zone will travel some distance. Okay, it will move forward, it will move in the forward direction, and when you see this rarefaction zone, there would be a compression zone close to it, because this compression zone has travelled this much distance. It was here only, but once this prong moves from right to left, in that time this compression zone has travelled some distance and it will move forward. Okay, so this compression will move forward, this compression will move forward, and similarly, now imagine what will happen when this situation is created, when the fork has moved from right to left. Now it is in left side. What will happen? When it again moves from left to right, that is again in this situation, again a new compression zone will get created. Okay, and this compression and this rarefaction has travelled some distance. Okay, and when it comes to the compression zone, like this situation, again this will move from right to left. That is, this compression will propagate in or it will get transferred to the next layer in front of it, and when it again moves from left to right to left, a new compression, a new rarefaction zone will get created, and this process will continuously repeat. So what you will find is that in this tuning fork, continuously adjacent compressions and rarefactions, okay, compressions and rarefaction zones will get created like this. Okay, continuously compression and rarefaction zones will get created. So this is compression, this is also compression, and so on, and these are the rarefaction zones. So these are the rarefaction zones, and this zones, compressions and rarefactions, will going to hit the ear of this listener, and he will be able to sense these compressions and rarefactions, and in this way he will be able to hear the sound that is produced by this tuning fork. So imagine the situation, what exactly is happening. The movement of this fork is creating compressions and rarefactions, and it is sensed by that ear, and in this way the ear is able to understand what exactly the sound is coming out of it. See what is happening in one complete cycle. When the fork is when this prong is in the left hand side, okay, it moved to the right and it again moved to the left. Once it moved to the right, it created a compression. When it moved to the left again from the right, it created a rarefaction. So we can say in one complete cycle, what is a one complete cycle? The movement of this prong from left to right and then again to the left. Okay, observe the situation, from left to right and then again to the left. We call this as one complete cycle. So in one complete cycle, from left to right and right to left, the prong has created one compression and one rarefaction. So here we will write this. In one complete cycle, from left to right and then right to left, the prong has created one compression and one rarefaction. Okay, it has created one compression and one rarefaction. So in this way, this prong will produce sound, and this can be heard to the listener. Okay, so imagine if there is no air present, definitely the compression and rarefaction will not be able to form, and if there is no compression rarefaction, the propagation of sound is not possible. Now as we have observed this this right sided prong, okay, so imagine the left sided prong, will it also produce the sound? Definitely. If it is moving like this, if it is vibrating like this, definitely it will also produce sound, but the propagation will be in this direction. Okay, it will move like this and it will propagate the sound in this direction, and the right prong will move like this and propagate the sound in this direction. Okay, that is, this will produce in the left direction, this will produce in the right direction. So this is how the production of compression and rarefaction happens. Okay, when the tuning fork starts vibrating, or when we speak. For example, right now I am speaking. So when I am speaking, continuously compressions and rarefactions, okay, compression zone and rarefaction zones are getting created, and you are able to understand, your ear is able to sense the compressions and rarefactions that I am creating. Okay, so that's why you can hear me. Okay, so it means the sound, this listening process can only happen when there is the presence of not only the source of sound but also the medium in which the sound propagates. Okay, so the basic concept to understand here, imagine two astronauts who are on the moon. Okay, so the two astronauts who are on the moon, they both have throat, they can speak, so they both can produce sound. Okay, but both of them cannot hear the sound of each other. Why they cannot hear the sound of each other? It's because there is no atmosphere on the moon. That means there is no particles which can propagate the sound on the moon. That's why the two astronauts who are on the earth can very easily talk to each other, communicate to each other, but when they are on the moon or any other planet which do not have atmosphere, they cannot communicate, because they have the source of sound, they have the listening power, they have the sound sensing organ, but still there is no medium to propagate the sound. So medium is something which is important. Now imagine when a tire bursts near you, you can hear its sound very clearly. Okay, you can hear a very loud sound, an explosive kind of sound when a tire bursts. But imagine there are stars present in the universe who are bigger than our sun. When they burst, we cannot hear any sound. Okay, when the star which is bigger than the sun, when it explode in the atmosphere in the sun, okay, or in the universe, so imagine what kind of sound, how huge amount of sound it has produced, but we cannot hear that sound. The reason is, in the space there is no particles which can propagate the sound. So this is the basic importance of medium, that how medium plays a very important role in the propagation of sound. It's good that you can hear, you can speak, so you have a source of sound, you also have a sound sensing organ, but if there is no medium, sound cannot propagate. Okay, and this is how the medium plays an important role. It continuously creates a compressions and rarefactions. Okay, so this concept is about compressions and rarefactions. Okay, so you can note this concept and then we will continue.